I'm going to get started since it's about time. For our first session today, we will have Professor Yuan Cao. Yuan Cao is an assistant professor of electrical engineering and computer science at the University of California, Berkeley. And he's perhaps best known for his research on superconductivity and twisted pair graphene in 2018, for which he was awarded the Physics Breakthrough of the Year prize, as well as various awards. He has continued figuring out the electrical properties of low-dimensional materials in its basic ways, as he will present in his talk today titled Real-Time Twistronics on a Chip. So without further ado, let's welcome Ben to the stage.
Everybody can hear me? Okay, so well, good morning and welcome. And it's my honor here to be able to give this talk in this summer school here. So, I want to kind of, tell you about what our recent research is about on this kind of on-chip real-time twisting. But before that, I also want to kind of give you a little bit of background on general, Twistronics and especially twisted bilayer graphene that my research has a lot of I have done a lot of research in the past on this front. And you probably already heard about this in the past few days at the times, but a large part of the condensed matter physics community are interested in these 2D materials, mainly because they have more tunability than their bulk counterpart. For example, if you take any of these class of materials and you look at their two-dimensional counterpart, they're always more tunable in the sense that for example, take any 2D material, you can put electrical gate to tune their charge carrier densities very easily. And furthermore, you can also stack these different 2D materials together into these so-called van der Waals heterostructures that provide you even more degree of freedom to play with their electronic and optical properties and so on and so forth. But of course, now we know that there is this extra knob that is the so-called twisting that can give you even more richness in the physics of these stacks of 2D materials or van der Waals heterostructures. And it turns out that this similarly simple twisting degree of freedom can actually give rise to a lot of interesting, strongly correlated phenomena, such as superconductors and also quantum anomalous Hall states or other type of magnetic states, also even like fractional state and so on. The first part of this talk, I will first give you a very short introduction of twisted bilayer graphene and how it works and why it kind of generates all these interesting physics from kind of experimentalist point of view, and maybe different from what theorists look at these problems, but just kind of give a also kind of chronological description of how these things are coming to play. So we all know about graphene. Okay, so graphene is this kind of carbon atoms with this kind of direct cone-like dispersion at low energies. Okay, so if you take two layers of them and stack them on top of each other, you get these. If they're not twisted, then you just get cones at the same location in the momentum space. But now, if you start to introduce a small twist, and what you start to see is that their direct cones are separated now in the momentum space by an amount that is equal to approximately k, which is the large momentum times the twist angle. Okay, now if you kind of look from different perspective, we have these two hexagons, and at the corner of these two hexagons, we can define the so-called mean equilibrium zone, which correspond to the periodic structure of the superlattice, which is like the large spot that you see on the Maury pattern. And now we take a line cut through these 2 points. Okay, so we're seeing now again these two cones. And now when you turn on the interlayer hybridization, which is like energy of about 0.1 electron volt, you start to get out this intersection between these two cones. Okay? And now when this interlayer coupling is on the same order as the energy scale that separates these two directions, you start to get this interesting regime, which is where magic things go on, and is where we find the so-called magic angle. Okay, and of course these are all thanks to the first description by distributed as McDonald, which is why the model is named after them. And this kind of summarizes this kind of short video, which shows you how the band structure of these two graphing evolves from a large angle to small angle. And at this special angle called the magic angle, we see this flat band, okay, where the dispersion becomes essentially zero. So let me just play this again. So at large angle, you're seeing these two sets of cones that are just from the two latest graphing, but at small angles, they start intermingling, and eventually at this magic angle, it becomes a flat band. Okay. And of course, this has like consequences in the real space as well. So at this, when you put your Fermi energy inside this flat band, what you see is that the electronic states are now localized in these so-called A spots. You can kind of think of it as the electrons, they kind of stuck in these spots with some hopping amplitude between the different spots. And this is what gives rise to all this kind of interesting, Coulomb dominated physics that happens in these materials. And because their kind of kinetic energy is now quenched when your Fermi energy is inside one of these flat bands. Okay. So now experimentally, what do we see when you actually study one of these twisted body graphing samples? Okay, so this is based on some work I did very early on in my PhD. But when you have these basically two layers graphene that are twisted at a large angle, okay, so let's say large meaning like larger than 3 degrees, and what you're seeing here is basically again these two sets of cones, right? And when you scan your Fermi energy through it, you see this big V-shaped curve. But now if we go to this intermediate regime where the bands are now significantly modified from the large angle regime, you start to see these energy gaps, right, that are created in the band structure. So these correspond to this dips in electric transport, because of course when you put your Fermi energy in this gap, you don't have any electrical conductivity, become an insulator. And where this happens, if you look at the x-axis, correspond to gate voltage where we convert to electron per mole would be +4 or -4. And the factor of 4 here comes from the fact that there is also spin and the value degeneracy here. So the take-home message is that basically when you feel +4 or -4 for electron or 4 holes into the system, you reach a gap state. Okay, and this is all single particle physics. Okay, so this exactly predicted by this McDonald model, and also other ways can make sense of this. So the most interesting happens now when you go to the so-called magic angle, which is 1.1 degrees, where you still see these large gaps that correspond to the single particle band gaps. But now what's extra is that you also start to see these extra insulating states that also occurs at +2 or -2 electrons or hole filling per mole unit cell. So this is pretty surprising when we saw this, because basically you're saying that the system is supposed to be a metal because your Fermi level is inside at the middle of a band, but you're seeing insulating behavior. Okay, so this is why we call this a correlated insulator. So there's an insulator that's not supposed to happen, but it now happens because of the Coulomb interactions between the electrons. And how do we know this, right? You can study, for example, the temperature dependence. This state actually disappears as you warm up the system, so that when the temperature scale is larger than the Coulomb energy scale, then it overwhelms that interaction. So you don't see it anymore. And how do we understand these states? Okay, so while there were some early debates about this, but right now I think the consensus is that basically you have when you don't have interactions, you have 4 copies of the flat band, which are you can call it K plus, K down, K minus, K prime up, K prime down. Now when you have periods, right? If it's in a flavor symmetric way, then field in that way, then you get a electrical conductor because you have a Fermi level inside the band. But now, if there is strong Coulomb interaction, then what can happen is that the system spontaneously kind of polarizes in this kind of so-called flavor degree of freedom, and now you're ending up with a gap state. And this state would have a lower energy than the original flavor symmetric state if there is strong enough Coulomb interaction. Okay? And actually, this doesn't happen only at a feeling of nu equals to 2, which is 2 electron or 2 holes per unit cell. It can happen actually at all integer nus, as long as the Coulomb interaction is strong enough. So, from an experimental perspective, how do we know this actually what's going on? Okay. Well, the earliest evidence for this is actually from the very early magnetotransport data in this magic angle twisted bilayer graphene, where you can see here that when the system is close to, I don't have the label of nu here, but well, just trust me that this region corresponds to around nu equals to 2, okay? And around that region, you're seeing quantum oscillations that have half of the degeneracy compared to normal graphene, which is 4. Okay, so this is how you know that when you're feeling electrons within this region, you're only feeling 2 Fermi pockets, and that corresponds to the 2 flavors that are spontaneously polarized. And this has been observed in many following experiments, with much nicer data quality, and also you can now start seeing that the same thing also happens around nu equals to 1 and nu equals to 3, where the degeneracy is broken down to 3 and 1, respectively. So further evidence comes from spectroscopy, okay, and much of this work has been done, here at Princeton actually, by the Yazani group. So you can see here that if you look at the the DIDV tunneling spectroscopy from an STM experiment on one of these AA spots, then you can also see that was a near Dirac point. You see this kind of characteristic, curve shape, but you see a replica of the same thing as nu equals to 1, nu equals to 2, nu equals to 3. Okay, so that's also evidence, that when basically you're polarizing the 4 flavors, and every time you polarize one flavor, the kind of Dirac behavior kind of reoccurs, and you're seeing a replica of this for 4 times in total. And there is also important evidence for this come from the so-called chemical potential measurements. So basically, in this measurement, you're measuring, the Fermi level, the absolute value of the Fermi level as you fill up the band. Okay. So basically, we call it mu versus n, where n is the density and mu is the chemical potential. Or you can also study the derivative of this, which is called the compressibility, dn dmu versus n. Okay. So when you look at this kind of same trend also occurs. So you see kind of replica of what happens near the Dirac point in total 4 times as you feel nu from 0 to 4 or 0 to -4. Okay. And in the raw chemical potential curve, then you're seeing kind of these dips, like kind of these modulations for also 4 times, reoccurring 4 times as you go from 0 to 4. Now the second, the next thing that happens is that what happens when we slightly dope away from the Mott insulator or the correlated insulator. Right? So if you familiar with cuprate physics, then you know that in this cuprate materials, which are Mott insulators when they are not doped, which is also another type of correlated insulator. When you dope away from them, you get this high TC superconductivity, right? And there's again a lot of debates about why that happens, but the fact that is in many condensed matter systems, this is what you kind of see that when you dope away from a correlated insulator, you get a superconductivity. So this is actually also what happens in this kind of twisted bilayer graphene system as well. And very surprisingly, what we found is that when you slightly dope away from this correlated insulator state, you also get superconducting state with TC up to about 2 Kelvin or so. There's a lot of following study on this about the strength of the superconductivity, the Perry symmetry, also about whether there is nodes in the superconducting state, which I won't go into in detail. But the kind of current understanding is that these are non-BCS superconductivity, which meaning that it's hard to believe that they can be described just from a phonon contribution, and that they have a kind of nodal structure there, which means that the density state doesn't go to zero at zero temperature. So just to give a kind of summary of the phase diagram in MATVG that we kind of know right now, this is basically a map of the filling factor versus temperature, where on the left side you have the very insulating band gap. On the right side you also have the very insulating band gap that corresponds to this and that. And within this whole region is that pancake that we looked at, which is the flat band. There are actually two flat bands, and each of them have a degeneracy of 4 from the spin and valley. And now if you fill up to +2 or up to -2, 2 electrons or 2 holes, you get this correlated insulator that disappears at some temperature, usually around 5 to 10 Kelvin. Now if you slightly dove away from it, you get this, superconducting domes actually on all 4 sides, okay, with varying strength and TC and so on. So there is also other phases that, just like cuprates, there are a lot of phases that are kind of unexplained, like this strength metal phase above the correlated region as well. That I also won't go into detail, but this is kind of well, actually, this I haven't updated this graph for a few years, but this is kind of almost up-to-date understanding of this material. So now, of course, this is just kind of vanilla twisted biography. Okay, so of course there are other things you can do to it. For example, you can try to induce magnetic states by some substrate engineering aligning with HV and things like that. So the idea is that now if you look at mu to +3, okay, where you have 3 states out of 4-state field, and it can also kind of spontaneously polarize into that state. Now you're left with kind of some net spin here, right? Because now you have 2 downspin field and 1 upspin is on field. So and this system kind of becomes spontaneously magnetic. Okay, so this is kind of what gives rise to quantum anomalous Hall state when you have a filling near equals to +3. And now in other related systems and also some non-twisted systems, you can also now induce fractional quantum anomalous Hall state now. The mechanism is slightly different, but still pretty much related to this spontaneous polarization spin. And the other kind of route to a different realm of correlated physics is now if you replace graphene with transition metal dihydrogenide, which are semiconductors. Well, this system, they have a relatively strong spin orbit coupling compared to graphene. Okay? So what happens is that now because of the spin orbit coupling, the 4 flavors, out of the 4 flavors, now only 2 are left near the low energy region that we're concerned about. The other 2 are kind of pulled out the energy. So then now you can think of like a multi-Harper model where you have some closer analogy to conventional strongly correlated systems, and where you have like multiple insulators and Wigner crystal and things like that. So this is also you can also see this in STM images. And, look at these kind of Wigner crystal states. So there's a different path of realizing correlated physics in twisted moraid materials. I also want to mention that outside condensed matter field, there is actually a lot of interest in twisted structures and their applications as well, especially in photonic crystals and also phononic crystal and so on. So you can use the same principles that we described here to, for example, engineering photonic flat bands or phononic flat bands that have applications in quantum science and other fields. Okay, so now I want to jump to the second part, which is where I think that the future of this field is going, which I think is the reconfigurability. Okay, so this is basically I'm talking about if we can realize the twisted material in a configurable way. So if you think about how, well, as an experimentalist at least, how I think about this twisting material is all of the devices we have studied is one of a kind. Okay, so every time you make a device, the twist angle is fixed, you can change it, and every device is slightly different. So this is really kind of unfortunate, and I think it hinders a lot of the interpretation of physics. So I think what would be nice is that if we can study these kind of materials in a way where the twist angle can become a real knob, where you can just change it as you measure. Okay, just like you change the gate voltage on a device, and you can change it reversibly, right? You can apply a voltage, and you can remove that voltage, you get everything in the exactly same state as before. So now there has been a few methods of doing this, okay, and all of them are based on AFM. So for the first method that came out was trying to push these kind of structures that are made of HBM graphene on top of another HBM graphene with AFM tip in contact mode. Okay, so AFM tip is something you can scan, and by scanning it in a controlled way, you can in principle twist two pieces of 2D material against each other. Although I believe it's not as controllable as you would want, but you can do this. And the other more kind of trendy way that appeared more recently is this so-called quantum twisting microscope, where you can actually now put one of the 2D materials onto AFM tip, right? And you can now, basically scan this tip just as if you're doing AFM over another sample, and you can basically perform like a tunneling experiment from the top 2D material to the bottom of 2D material. You can study, or you can do this as you change the twist angle, right? Just rotate the sample, and you can kind of figure out the twist dependent tunneling, which reveals information about the band structure of the underlying graphene. But of course, we want to do this, in low temperatures and high magnetic field and so on and so forth, right? So, now when you want to do that, that's become a little bit complicated. And I know people here at Princeton know how to do that. You guys are experts, but unfortunately, I don't know how to do that. Especially in low temperature and high magnetic fields, okay? And this is something that I think, only a couple of groups in the world know how to do. So, I have been thinking, can I do this without, what you guys have? And, can we do this in a way so that the twisting just can be made as simple as, electrical gating, okay? So just put a gate voltage, put some voltage, and you can just rotate to 2D materials. At the same time, I want to have the advantage of having a high quality interface being versatile, meaning that I can perform more than one type of experiment. Having accessible interface, meaning that you can do more than just one type of thing to the interface, like for example optics, right? And also robust, meaning that you can put this device into low temperature and high magnetic field without interfering how it works. So now if you put all these constraints together, and again, of course, there's also one constraint that we want to keep the thing as simple as possible for the users, right? Then there is actually not many, or there is no available technology to do this. So I guess then I have to invent something new, right? So with that as the motivation, we have been working really hard in the past few years to kind of develop this new platform, which we call Mega 2D, which is like a new type of device which allows this to become the truth, to make this kind of dream come true. Okay. So this is like a device that is based on the so-called MEMS technology, which is devices that exist in all of your smartphones as accelerometers and things like that. But we have been adapting this technology to do now Twistronics. So this is a device that we designed from the scratch to include all those capabilities that I was talking about that we want to include. So right now it is capable of adjusting the twist angle and also the distance between two pieces of ultra flat 2D materials. And that's the entirety of what this device can do. Okay. Now if you take a closer look at what this device is, it has two parts. So one part is this MEMS chip. Okay, it's like a silicon chip that as long as we apply some voltage onto it, you can do the motions that you just saw in the video. And the other part is the substrate, which can be any material in principle. Okay? And we assemble these two chips together, and that's our device. So, and this device is, designed to be, compatible with, low temperature and magnetic field from the scratch. So, we can operate this device at, cryogenic temperatures, even millikelvin without any problem. Okay, and also high magnetic field, because it's not based on, any, coils or magnet or things like that to drive it. It's based on a completed electrostatic mechanism. Right? So now where we put the 2D material. So if you flip the chip, we have this pyramid that is kind of etched onto the back of the silicon tip, where now we can put down, the 2D material that we want to study. Okay, so this is what it looks like when the 2D material is tented onto this pyramid. Now, this is because this is kind of technically from a very different field. So I want to also take a few minutes to, tell about how we actually made these devices in, university clean rooms and that, and why it is advantageous to do this in this way. Okay, so the starting point is this commercial wafers that are so-called SOI wafers, which have 2 layers of silicon and separated by silicon dioxide. Okay, so we first etch this pyramid, okay, from the backside of the wafer, and you'll see in a moment why it has to be done in this particular way. And now we etch these kind of so-called TSVs, which are for electrical connection, which is not important here. And we etch these kind of trenches from the back, we etch these trenches from the top. And then the final step is called release, which means that you kind of etch away these silicon dioxide layers so that the whole device becomes suspended, so now you can move, right? Now, if you look at this interface down here, the flat surface at the top of the pyramid, this is actually the intrinsic surface of the wafer, okay? Meaning that it is polished to be extremely flat, just because it's like a semiconductor grade thing. And we actually measure this roughness to be less than 0.2 nanometers. And it's even flatter when you put a layer of HB on top of it, okay? So this is very important for 2D material studies, because of course you want flat interface to start with, right? So, and this is how we guarantee that to be the case. And the final assembly is, we take one chip that has already a layer of 2D material transferred onto the bottom of the tip, right? And then we put this and assemble it together with the substrate, which already have another layer of 2D material that is pre-transferred and cleaned there. Okay, so this is the complete device. And it's about 1 centimeter in size. So you can put this into any apparatus, or take this to MagLab or things like that. What I want to emphasize is the entire device, and basically now you have is a tunable interface between 2D materials, right? As long as you put some voltages onto the MEMS chip. And this is a picture of the actual device. So what I want to emphasize here is the firstly versatility, which is because the chip is very small, you can put this anywhere, right? You can also even put this into, I don't know, maybe RPES. That's one of the plans we want to do in the future. And the other thing is accessibility. So the substrate is transparent, which means that we can do optics, and we can even further engineer the substrate so that we can kind of fully suspend the device and things like that for other type of experiments. So just to summarize what we currently have, so for example, you can see here that's the Mega 2 device under operation. You can see the in situ rotation, and you can change the distance between the 2 layers, and you can see here that's kind of manifested as the autofocus in focus on the microscope. You can use the central pillar as a top gate, okay? So you can put gate voltages very easily. And from the bottom, you can access by optics, standard optics. So this is actually a video that shows you that 2 HBM flakes that are being twisted in real time. Okay? So we can twist about 20 degrees in total. And finally, we can also engineer the substrate so we can do actual transport, okay, under the tip. And this is actually quite important. And well, I think this is something that, maybe one advantage compared to QTM is that we can use much larger tips, and we can, in principle, do this, in situ transport as the twist angle is varied. Yeah, so this is just a comparison of the mega 2D versus the QTM kind of type of experiment. Well, I just jump to some experiment we have been performing using this new platform that we developed. So well, just to show you that this device actually works, right? So this is showing some optical response if you just shine a femtosecond laser into two pieces of HBN that are being rotated and pressed against each other. So what you can see here is that there is this kind of oscillation as you approach it, right? And this is actually quite expected because there is optical interference, right? So every time the signal kind of oscillate by one period, that corresponds to exactly half of the wavelength of the laser we use to excite. But we can use this to kind of very accurately calibrate how far the two pieces of 2D materials are from each other. And as you can see here, that once they touch, then the signal stops changing, right? And above that point, you're basically starting to apply pressure, which we haven't really tried to press very hard, but you can in principle push it up to hundreds of megapascals or even gigapascals using this method. And now, because we have this kind of very nice capability of optical accessibility, we can actually categorize the 2D interface using optical method. Right? So here, what you can see is that this is the ACG map, which is I'm going to talk about ACG later, but basically a way of categorizing the interface so this is the image before the two flakes are engaged. Okay, so they are still spaced by 1.6 microns. Now, when we apply the voltage to drive the MEMS down, they are now touching, and you can see that okay, the signal has changed, and there is a little bit of inhomogeneity there, presumably because there's some bubbles trapped between the two HBNs, which is pretty common when you work with these 2D materials. Okay. But what we can do is that once it's in contact, we can kind of twist a few times. And that actually acts as a way of cleaning the interface. And this is also something that people have been knowing for a while, which is called the self-cleaning of 2D interfaces. Because these are automatically flat interfaces, they try to maintain the flatness. And if you kind of squeeze a few times, you can squeeze out the bubbles. And we can actually check that is the case by doing this optical measurement to see that the interface is not free of any inhomogeneity that at least that we can detect. And the other thing we can do is we actually now measure the van der Waals force between the 2D interface. Okay, so people talk about these van der Waals scalar structures all the time, but not very often people actually talk about the force that bond them together. Okay, so van der Waals force is not chemical bonding, right? So it's a relatively weak force, and we can measure that force basically by looking at the hysteresis, okay, when we approach the MEMS and then we retract. And we kind of monitor the optic signal, you can see that there is a kind of significant hysteresis. And that's because once the two interfaces touch, then if you want to pull it up, you have to apply some extra force because the interface is pulling it down. So basically from the size of this hysteresis, you can estimate the force that is bonding them together. And this actually will, for this particular sample, it's estimated about 4 megapascals. Which is like, I guess, well, definitely much weaker than chemical bonding, but it is kind of on the same order of magnitude than as the force that is required to exfoliate the flakes and so on and so forth. So far we haven't turned on the twisting yet, right? So now we should do that. So one thing that you immediately see when you turn on the twisting is that twisting actually breaks the mirror symmetry or chiral symmetry, right? So basically, a structure with left-handed twisted angle and the plus or minus twist angle, they have different tenderness, just like left or right hand. So you can detect this by optical waves. Basically, these different structures, they will respond differently to left or right circular polarized light. And this actually has been seen almost a decade ago. This is actually in twisted bilayer graphene. And you can see there this so-called circular dichroism, which is the difference between the reflectivity of left or right circular polarized light, is a little bit different. And you can detect this, and they're opposite for opposite twisted by graphene. Okay. But of course, back then there is no mega 2D, so you have to, or QTM, so you have to do this, in many different samples, right? So each curve is basically a different sample. And now we have that capability that we can do this in a completely continuously way. So we can see this inversion of the second harmonic generation circular dichroism signal. It's like antisymmetric as we go through 0 degree of twisting angle, just as one would expect. So I want to say a few more words about SAG, which is second harmonic generation. So this is basically referring to the generation of basically a 2 omega optical light when you kind of pump it with the omega. Okay, and the reason why it generates 2 omega is because of the nonlinearity of the dielectric or sample that you're pumping into. Okay, so this is described by this so-called chi2, which is the second order nonlinear coefficient of any particular material. And this is non-zero only for materials that have broken inversion symmetry. Okay, so meaning that if you just take graphene, there is no chi2 because it's an inversion symmetry material. But any HBN or TMDs and well, most other 3D materials, they have non-zero chi2. So if you take HBN, for example, and you can now measure the second harmonic generation as a function of the polarization, right? So and you're expected to see this kind of cosine square 3 theta behavior, which just looks like that. Okay, so we call it a flower, but it's like a 6-fold symmetric pattern that is very typical in this material. So and that kind of corresponds to a lattice already like this. So the maximum of this load, they always correspond to the the axis with the mirror symmetry. Okay, so for example, that direction is the direction of the armature. And along the armature, you have a mirror symmetry of up versus down, right? And this is for parallel second harmonic generation, meaning that you're kind of having the same input and output polarization that you detect. So now when you put two plates together and you twist them, right? As we said, you break the symmetry, and now we want to know how that symmetry break affects SAG. Okay? And there is some, actually you can derive all this from a group theory, point of view. So, but just simply speaking, if you take graphene, which you have like a higher symmetry for these 2D materials, right? There is no SAG, and because the chi2 term that's relevant is kind of prohibited by the group theory. Okay, so if you have this high symmetry, now you break the symmetry, okay, into this 3CV, which is for HBN. Now you start to have this SAG, and I call it a single component SAG because the entire pattern is described by a single, nonlinear self-stability chi. Okay, and now you can further break the symmetry here. So the more you break the symmetry, the more terms are allowed in the nonlinear tensor. Okay, so here you only allowed one single component to be non-zero. But if you now twist 2 layers of HBN or any 2D materials that have nonlinear response, you're breaking the symmetry down to C3, for example, right? Because now you break so that V means you have a vertical mirror plane, right? Now you break that mirror plane by twisting 2 layers, and you're now breaking that symmetry into C3. And in that case, you would be expecting the flower that would look very different than before. Now the minimum doesn't go to 0 anymore. And this is what I call 2-component SAG, because now to describe this, you actually need 2 independent values, okay, chi1 and chi2 to describe this thing. So in principle, if you further break the symmetry into something completely different, then you can even get more terms. It gets even more complicated patterns. Okay. But at least for our purpose, because we are studying this twisted 2 layers, right? So this is kind of where we will stop here. Now, if we will kind of look at this modified 2-component flower, right? You can actually extract the chi1 and chi2 in an exact mathematical way. Okay, so And you can actually map that into kind of a vector on the plot sphere in some sense, because now you can write down this chi1, chi2 in kind of a spinor form. And that's why you can basically kind of define this pseudo spin, right, from the chi1, chi2 response. And it has kind of a mapping relationship between like a flower like this to a point on the plot sphere. This function f here is, some like arctangent, just too long to put into the graph. So why we are mentioning this is because now, okay, we have these two flakes, right? And the distance between them and the twist angle between them are two knobs that we can control, right? So basically, we can now think about, what is the kind of nonlinear susceptibility of the entire system as a function of the, h, which is the distance between the two flakes, and the theta, which is the rotation twist. So now you can do this actually in a theoretical way. So if you plot the color, basically meaning the that's kind of the azimuth of this vector. Okay, so goes from 0 to 2 pi. So you can plot the azimuth of this nonlinear susceptibility vector as a function of the h, which is the distance, and the theta, which is the twist angle. And you see this kind of nice color plot with some peculiar features that we go into. But one thing that I want to mention is that, well, this is actually a periodic function as a function of both h and theta. Okay, so in some sense, this is called a synthetic Brillouin zone. Okay, so because the topology of this system is you can map that to a two-dimensional Brillouin zone. It has the same mathematical structure, right? It has like this bi-periodic structure as a function of both the x and y axis. And what we're plotting here, like each point, you can define kind of like a, well, it's kind of a spinor, right? So this is why you can map this kind of onto a system where each point is like a pseudo spin, and you can define all this topology stuff in there. So now, if we look in further detail at this singularity point where there seems to be kind of some winding of the phase, right? If you plot the actual spinor at those points, you actually see this kind of thing that looks like maron, which are kind of half skirmious, or it's kind of like a vortex of this kind of pseudo spin, right? So you can actually classify these different vortices using their the direction of the winding and whether it's pointing up or down at the center of the singularity. And there are in total 4 types, right? So each of them have some topological charm associated with it. But I want to say, if you look at what intuitively is happening around this singularity point, right? So if I park at that red spot where it corresponds to 0 degrees, what that means is that if I shine in a linear polarized light in the system, I would get a linear polarized second harmonic light out, which has the same polarization. Okay? But if I tune my parameter, which is h and theta, but if I tune them kind of in synchronization around that point, and I kind of rotate that around that singularity by 360 degrees, the polarization of my outgoing SAG light rotates by 180 degrees. Okay, so that's basically what's happening around this singularity point. And now if I go to a different singularity, let's say the yellow one, where the winding direction is opposite. Now that if you do the same thing, the polarization will rotate around the opposite direction by 180 degrees. Okay. Now, what if I directly go to one of these singularities? Now, what's going to happen is that although what I'm putting in is a linear polarized light, what I'm getting out is actually a perfectly circular polarized light. Okay. So, which basically means that my flake or 2 flakes here is now imparting some chirality into the light that is generated through this nonlinear process, which is expected because the system is chiral, right? As we said, when we twist them, it becomes a chiral thing. If you don't have any twist, then this is never going to happen. Now, of course, because we have these 2 knobs continuously, we can map out the entire thing in an experimental way, right? So we can actually see these singularities completely, and we can characterize them to look at their behaviors, like can measure the basis of flowers at each point of them and extract the nonlinear susceptibility there. And we can match pretty well with the theories. But I just also want to mention that, this seems to be a mathematical game, right? But what we can actually do is we can actually find some, certain applications of these kind of topological singularities, which is one of these, polarization-tunable light source. Okay, so just imagine that if we want to have a device where we, shine a fixed polarized light, and just by tuning the internal degree of freedoms without changing anything about the input light, we can now generate any polarization just by tuning these two knobs. And we can tune into any polarization possible, which is basically any point on the block sphere. So we actually demonstrated this in this setup where we can tune this theta and h in this kind of accessible range, and we can reach all of the important polarizations like vertical, horizontal, 45 degrees, or circular polarized light, and almost any point on the block sphere, or basically any elliptical polarized light using this device. And you can also imagine doing the opposite. Okay, so this is from a very different field, but I think it's pretty interesting because now if you think of doing the opposite, which means that you shine in now a 2 omega light and let it generate omega. Okay, so this process is called a spontaneous parametric down conversion. Okay, and it's actually intrinsically a quantum optical process. So what you generate is this kind of entangled photon pairs. And now if we do this in the same method as before, by tuning these two knobs, now we can realize quantum light source where the entanglement and the polarization of the entanglement is now tunable. Okay, meaning that if I look at this block here, now the poles are non-polarized light. Okay, non-entangled light. And on the equator, I have two types of entangled light. One is up minus, like horizontal minus vertical, or I have horizontal vertical minus vertical horizontal. Okay, so there's two types of entangled photons, and I can also in principle tune into any points on this block here, just by doing the same game as before. So this well, almost the end of my talk, but I just want to mention that this is the start of kind of a new subfield where we try to use this kind of new MEMS device to tune to the materials. And so far we have demonstrated this kind of nonlinear optical properties. But what we can do is much more than this. We are trying to also study this kind of twisted excitonic behaviors, of course superconductivity as well, and also this topological state like fractional quantum unknown Hall state using these 2D materials. And in the meantime, we're also developing new type of these mega 2D devices where we can basically firstly incorporate more degree of freedoms, more than just the z direction and the rotation. We can also basically now start doing scanning as well. And we also have been working on developing suspended devices where we can access the 2D interfaces from the backside of the substrate, so that we can say do RPES and maybe TEM and other type of studies. This work was appeared on Nature last year. So if you have interest in details, you can look into that paper. And yeah, with that, I would like to thank everybody that worked on this project, and this is my current team at Berkeley. And thank you.
Thank you, Professor Cao. This is a very nice talk. And I have two questions. One is about the detail of your twist device, right?
Mm-hmm.
So in your device, you put one layer of material on the tip of a paramoid, and have you characterized the like strain on that device, like by Raman spectroscopy, something like that?
Yeah, we did measure the strain, not by Raman, but by we actually measured the, basically we put some dots on the plate before transfer, and we measure the same dot after transfer. We can extract the actual strain. So we can perform like well, the strain is pretty well controlled, I would say, because it's kind of tented in kind of controlled way. It's like less than 0.2% or something. Yeah. Does that answer your question?
Yes. And my second question is like, I'm very surprised by the capability of your new mega device, and but in this device you can like change the twist angle between the two layers, but not many there are many works on the like tri-layers or 4 layers. And also most transport measurement that involves not only the twist layer but also the gates, right? And is there any limitation of your device on the transport, like these kind of things?
Yeah, so there's no limitation on gating, right? So we can use the tip for gating for one thing, and you can put whatever bottom gate, right? That doesn't really affect the operation of this device. So in terms of the layer of, so you basically you have one device, like you can control one interface, right? So you can distribute how many layers you put on the pyramid and how many layers you put on the substrate, right? So as long as you're only twisting one of the interface, then you can use this device. And in principle, you can twist 3 layers device. It will be more, basically you can more like up in the skies, but you can think of putting 2 of these devices, one on top and one on the bottom. You can twist 3 layers. It'll be hard. So yeah.
Thank you.
Yeah, thanks for a really nice talk. I was wondering if you could say anything about how, I guess you could say like coplanar, the tip of the pyramid and the substrate underneath are, like how flat these two materials being tested?
Yeah, that's a very good question. So we have been doing those calculations very carefully. So we can achieve something around 0.0 degree of tilt angle between the 2 interfaces. So which translates to about at most 1 nanometer difference between one side to the other side. Yeah. So that's kind of by calculation. But what I understand is that at those scales, everything is kind of soft and squishy. So if you apply some pressure, even if there's a 1 nanometer gap, you can close it pretty easily.
Just one other question. When you talked about you can sort of embed some like Hallmark contacts or something for doing transport measurements. Are those actually sort of entirely on the flat part of the tip, or are you going to be sort of?
Those are on the substrate.
Oh, they're on the substrate.
Yeah. Yeah.
Okay. Are you accessing just the region of material basically where they're actually in contact, or are you going to end up averaging over some of these like regions?
Yeah. So so we can make the tip to be very large. So right now it's about 4 by 4 microns. We can even make it larger. So you can basically try to make well, if you make the whole product smaller than that, then you can make sure that you're only accessing the twisted region.
Maybe a naive question. Can you tunnel currents from the tip to the bottom layer?
Can you do tunneling?
Yeah, do tunneling.
Yeah, of course. So basically the tip itself is a conductive post, right? So you can either use it for gating to put into it, or you can directly tunnel it to the substrate if you just put your right on the tip. Yeah.
So you can, in principle, also do things people doing
the QTM.
Yeah.
Yes. Yeah.
Have you done that with measuring some?
We haven't done that yet. Yeah. So we have been pushing on the transport mostly, and optics. Yeah.
Hi, very nice talk. I also have a detailed question. So the center of the pyramid is suspended on the device. When you transfer 2D materials onto the tip, was the tip easy to break, or
No, it's actually pretty robust. Like never break during that step. Well, unless you press really hard. Yeah. So we have a way of basically you just release your stack there without pressing too hard. Yeah. Just don't press. Yeah.
If there are no further questions, let's give a round of applause for questions.